Welcome back. This is the second video on a quick shifter for a Yamaha R3. In this video, we are going to look at how to detect the ECU when it's getting ready to fire the coil and also when it fires, so we can delay it whenever we need to change gears. So we're going to start by looking at the profile of this connection when it's getting ready to fire and when it fires, when the ECU sends the signal. So the way it's supposed to look, if everything was perfect, it would be, we will have a 12 volt rail, and then we will have a 0 volt rail. So when the ECU is going in ready to fire, it pulls this connection to ground. So the connection here, or the profile, looks like this. And when it fires, it disconnects it from ground, so the voltage is supposed to go right back to 12 volts and continue. Now, because this is an inductor, there'll be spikes, huge voltage spikes that we need to account for. And the profile for that, the actual profile of this connection looks like this. Again, we have the 12 volts and the 0 volts, and it looks like this. And when it disconnects it from ground, the voltage shoots up and it goes all the way down, up again, down, until it stabilizes. Uh, on this unit, on this one here, the one we did on the last video, the voltage is going at 700 volts. So if we were to detect this connection here, it will give us this high voltage that it would burn everything, all the electronics that would attach to it. They would become disabled immediately because of the high voltage going up and down. So we need to put something in place to remove this section and don't let it go past the 12 volts. And actually, we're going to bring it down to 5 volts to a voltage that we can manage with our processor. So to do that, we are going to uh, use a resistor. It's going to be a 10K resistor, and we're going to use it in line with a diode. And this is a Zener diode. This is a 5 volt. So what it's going to do is it's going to sink all the voltage to ground, and it's only going to allow to have 5 volts at this connection. So the profile here, if we leave it like this, it would be more manageable, but still we need to do a little bit more to smooth it out. So the new profile at this point would be, now we will have 5 volts instead of 12. And we end up with something like this, where it eventually stabilizes. So what we're trying to do here is we're trying to detect when the voltage goes down and when it comes up, so we can determine how long it took for that spark plug to be, or that coil to be pulled to ground, so we can delay it. So we want to change gears. We, instead of, let's say this is 2 milliseconds, we want to put it to 2.5 milliseconds or 2500 microseconds. Then the profile would look a little bit like this. Um, the problem with this is that because we're detecting when it goes down, this will create a false positive, and this will create a false positive, um, and we will lose the actual time here, and we will only have this. So if we try to change gears, the profile on our unit would look like this, right there, and the next one there. So it would be ineffective because the ECU would still have it down. So we need to do a little bit more. We need to put a low pass filter. And the way we do that is we put a capacitor. And it's going to be a 0.75 0.33 microfarads. By the way, the math to calculate the low pass filter um, is 1 over 2 times pi times resistance times capacitance, and that will give you the cutoff frequency. This is a little more involved in that. This is the basic calculation, and because there's other components around this capacitor or this filter, the the value is a little bit different. But so now that we have this, what this will give us a disconnection. So we have one output here, and then we have another output here, and now we have our new output here. So this one was giving us this, and this is giving us this, and this is going to be the new profile, which would be 5 volts, 0 volts, and now the profile will look like this. It will be something like that. So that's a little better. We don't have the ringing anymore, but this section here is not that clear. So and also because we have ringing here, and sometimes it's pretty high, that it may dip below 1 volt. It may end up creating a false positive every once in a while. So that's still not good enough. Also, it's hard to tell when the signal becomes low. Is it here, or is it here, or is it here? You don't know. So we need to add a couple more components to make it clear, and we want to reverse the signal so the ringing is at the ground part and not at the voltage part. So if there's any issues, it will ring to ground instead of ringing high voltage, or bringing the signal down. Since it's already down, it won't matter. So what we need to do here now is we are going to use a transistor. This is the same transistor we use on this unit. It's this right here. It's an NPN 222A transistor, and the way we are going to connect this will be like this. And this one has the 3 legs, and it has the emitter, the base, and the collector. Emitter goes to ground, same as before. The base the base is going to be connected to this uh, connection here, 10K resistor, and the collector here will be connected to voltage, 10K resistor as well, 5 volts, and the new output is here. So this is where we are going to detect the signal, and the signal here should be um, a clean signal, and it should be in reverse. So when this goes to 0, we should have a positive 5 volts uh, rail. So what the signal is going to look like, we have the 5 volts and we have the 0 volts. So the way it's going to look now is it's going to go like this, and somewhere around here it's going to go straight up and then straight down and keep going. So that's the signal we want. We want to detect the amount of time it did this. It went up and it came down. So when we're ready to fire, and this is going to be on the next video where I'm going to show you how to detect this, and also how to extend it whenever we are ready to fire, so we can keep extending it. And once the gear goes on, then we can go back, so we can make it a smooth transition to the next gear. So let's create this connection. So this is the old unit that I had, and we are going to start by simply firing the coil and showing you what it looks like at this point right here, so you can see this signal here, all the ringing that goes with it. So let's get our coil. There is the coil. I'm going to plug it to ground. into voltage. This is the one for detecting the signal. Let's see, let's turn this on. There it is. So let's see, we have spark. What are we missing? Ground. Let's go to ground. Oh, of course. 12 volts. There we go. And there is the spark. I don't know if you can see it, but I can sure hear it. All right. So now let's see what it looks like. So let me power on. Let me adjust the signal here. So there's the signal. It's at 10 volts per division. You can see that the voltage is pretty high. If I go to the maximum, it's reaching almost 700 volts right here. Anyways, so there is the signal. You can see all the ringing, especially right there. There's a lot. Okay. Oh man, what happened? Did I lose my connection again? Uh, Hold on. The the EMI, is it called EMI? And all the static that is coming from the spark plug is killing my connection from the phone to the computer. So let me see if I can get it back. Okay, let's see if it's gonna kill it again. All right, so there it is. There's the signal. You can see it looks just like this right here. Now we're gonna go to the next step and make it look like this. All right, so we said we need a 10K resistor and a Zener diode. So There it is, my 10K resistor and my Zener diode. And now the signal should look like this one. So let's take a look. So there it is. You can see the ringing down there is no longer shooting up, and it's at 5 volts. You can see there's a 5-volt division. There's the ringing. All right, so now we want to get rid of that part. Let's turn this off. And let's add the additional components. It's oh, we forgot one here. There is an additional 3K resistor that goes here. So the 3K resistor. Here's a 0.03 microfarad, 33 microfarads, and they are going to be connected to ground. There's a capacitor and the resistor. Now let's see what it looks like. There it goes. So there's the signal. It's a little bit better now. There's no ringing going to the bottom, at least not far enough. And you can see this is well above 2 volts. So now let's do the next step, which is reversing the signal. Now we have this. So we went from this to this. We're at this point. Now we're going to reverse it to this. So for this one, we are going to need I don't know if this is a 10K. Yeah. Let's put it back the way it was. Like that. And now we need a transistor. So the transistor goes like this. It's going to be from a 10K resistor. So let's put an extension here first. There. Okay. That resistor goes to the base. The emitter, the transistor is facing me, the flat part is facing me. So the emitter is on the left, and that one goes to ground. And the collector goes to 5 volts. And now we should have a signal right here. So let's see what it looks like. There you have it. Pretty clean. So let's put the two signals together, the original one and the new one, so you can see uh, what it looks like with the high voltage, and once we have all of those components in place, filtering it out. So let's look at the signal at the coil and the signal at the transistor. So let's see. So the blue is the signal at the coil. You can see the huge spikes, and the yellow is the signal at the transistor. You can see that it's pretty clear. Now, the reason we're not detecting that ringing and the ringing here is because the filter itself is creating a delay. You can see the signal is shifting a little bit, so it's shifting enough that is the width of that ringing. So let's look at it on the switch on. There we go. So you can see that the delay is about just over 100 microseconds, which is it's manageable. The signal on the R3 is usually 4 milliseconds, so 100 microseconds is nothing. But we're only concerned with the length of when it goes up. When it goes down, it will be consistent with a 100 microsecond. Uh, but the up is right on it, as you can see. There it is. So there you have it. So what we did is we added a, well, I have a cleaner version here. Um, we added a 10K resistor to a 5-volt Zener diode. A 0.033 microfarad is connected to ground, and then a 3K resistor connected to ground, and then we have a 10K resistor going to the base of the transistor. The emitter is connected to ground, and the collector has a connection to voltage through a 10K resistor. And this is where we're detecting our signal. On the next video, we are going to use the ATmega 320A processor to detect the signal, and also uh, to uh, to increase this signal even more. So let's get one of the other drawings. Let's see. So on the when we have the ATmega, we are going to have another switch on that processor as well, because we want to delay it. This is only for detecting the signal. So along with these components, we are going to have these other components to delay it. So the signal is going to come to here, and also going to go to, so this connection is going to go for this one and this one. So it's we're gonna have essentially two two connections, one for detecting and one firing. So once we detect the gap and we want to extend it, then we're going to use this one to the ATmega. Is going to be connected to this pin, and we're going to hold it down longer than the ECU. So instead of the signal coming down here, it'll be a little bit later and a little bit later. And we want to we want to create a smooth transition where it just expands little by little. Let's say in 5 steps. So it'll be, the cylinder needs to fire five times before it goes to full loss of power on the motorcycle, and then we're going to bring it back up. And the way we're going to bring it back up, it'll be up 80% immediately, and then smooth it out towards the end, so you can feel the kick, but not too much that it unsettles the bike. So here's the first one. That's how you control a coil. There's the full page if you want to see it. There's the well, there's the code, the connections to the coil, all the way to the connections. Those are the connections we have here. This part is just this connection and the processor, the transistor. And what we did today is this connection here, which is again the 10K resistor, the Zener dial, capacitor, resistor, and the transistor. So that's all I have. See you on the next video.